All right, welcome everybody. Before I hand over to the session chair, I want to welcome all the new people here and warn you of the fact that we seem to be a breeding ground for COVID here. We had many cases at the end of the second week, at least 10. We seem to have many cases again now, including our current speaker. Hope you're doing okay. Yeah, so ground rules, you can't be in this lecture hall without a proper FFP2 N95 mask. If you don't have one, the office has them. You can just pick one up at the office. So please, actually, if you don't have a proper mask, go there now and get yourself one. And you need to be wearing it. You need to be wearing it anytime you're in here. I can't enforce it anywhere else, but please wear them whenever you're with a lot of other people. Yeah. A lot of those cases seem to have come from things that happened away from GGI. You're not immune just because you're not here. So consider, the effects of large gatherings in small apartments or Airbnbs. And what else? Yeah, we have, so in addition to free masks, we normally have free self-tests, home tests, rapid tests, which you can also pick up at the office. I think we ran out today because of high demand. So hopefully we'll be back in business tomorrow, but if you need to, if you feel like you want to test today, you can get them any supermarket, any pharmacy. They're very cheap. So yeah, I think that's it. I do want to stress that this is kind of important because we don't want our workshop to be shut down. So let's all do our part. All right, and with that, let me hand it over to Adam.
Okay, today we have Aasmund, and he's going to tell us about canonical purification of evaporating black holes.
Okay, so let's see. Yeah, so first, of course, thanks to the organizers for organizing this great workshop, and thank you for the invitation to speak. So I was, of course, hoping to do this talk in person, but as usual, COVID ruins all the fun. To be kind of light on my throat, I'm going to try to keep this a little bit shorter than what was first planned. Okay, so I'm going to tell you about canonical purification of evaporating black holes. And this will be based on a paper from early this year with Netta. So a major goal of ADS CFT is, of course, to try to extract the gravitational picture directly from a CFT quantum state. And two slogans that kind of capture a lot of what we know about this process is entanglement builds spacetime and ER equals CPR. These are, of course, related, but not necessarily the exact same thing. And kind of the prototypical example that exemplifies both of these slogans is the ADS Schwarzschild black hole, which is dual to the thermal field double. And of course, the thermal field double is constructed by entangling the energy eigenstates of two holographic CFTs in this way. And to the extent that each energy eigenstate has a holographic dual, this holographic dual has to be some disconnect to one-sided spacetime, or just a one-sided spacetime. So we see that in this process of entangling these CFTs, so taking the sum, we're building some kind of connection. And of course, in ADS CFT, we know via the QES formula that wormholes imply entanglement. So that just follows easily from the QES formula. Whenever there's a wormhole, there has to be a non-empty dominant QES. But the question is, when can we flip the arrow? Under what conditions does entanglement imply a wormhole? So I'm going to consider two proposals now that aren't a strict converse, but maybe are somewhat morally potential converses. So consider some quantum state on some tensor factor Hilbert space of two holographic CFTs, HA times HB, and consider the following proposal. I'm gonna summarize it quickly by saying semi-classical highly entangled states are always wormholes. So specifically, assume that psi has an order 1 over Gn entanglement between A and B, and that psi has a semi-classical dual. Then the semi-classical dual is connected. This seems fairly reasonable, but it's false. And we'll give some pretty basic examples showing that this is false in this talk. So let's consider another proposal that I'm going to call ER equals EPR. So assume psi has an order 1 over G Newton entanglement between systems A and B. Then there exists a factorized unitary, UA times UB, such that the state, after acting with this unitary, has a connected semi-classical dual. So this is maybe kind of the weakest interpretation of ER equals EPR you can imagine. There might be stronger versions, but everything I'm going to say in this talk is going to be consistent with this statement being true. So to kind of justify calling this proposal ER equals EPR, I'm going to read a quote from the original paper. So if an observer collects the radiation, then with a powerful enough quantum computer, she could collapse it into a second black hole, which is perfectly entangled with the first. In addition, by operations solely on her side, she can put the pair of black holes in the special state that produces the smooth ER bridge. Now, we're going to show generally that this quote is true after page time, but that it needs a slight refinement before the page time. And that's related to this statement that I've highlighted here, solely on her side. Okay, so in our paper and in this talk, we construct a general procedure to realize ER equals EPR after page time in evaporating ADS black holes. We carry out the procedure explicitly in JT gravity. We show that the highly entangled bipartite CFT state with a semi-classical dual need not be a wormhole. And we argue that the reliable CFT diagnostic of space-time connectivity is lacking. Okay, and here are some other related works. It's investigating the connection between ER equals EPR and these novel island QESs. Okay, so the toolkit. So really the main tool we're going to need is the canonical purification. So what's that? It's a special map of a mixed state on a Hilbert space H to a pure state on the Hilbert space H times H. So if we expand some density matrix in some basis I here, then you can write the map like this, where the I star is just I with a CPT conjugation applied. This looks basis dependent, but you can show that it's not. And the kind of prototypical example of this procedure is if you canonically purify the thermal state in the canonical ensemble, you get the thermal field double. Now, the very useful thing is that we know the bulk dual to this procedure. So given a mixed state rho on a complete boundary time slice, the dual to square root of rho is given by gluing the entanglement wedge to a CPT conjugated copy of itself. So let's just show this in pictures. You start with some entanglement wedge dual to some CFT state rho. You have a QES chi. Then you introduce a second copy of the entanglement wedge. You do a CPT conjugation, which essentially flips the wedge on its head because it includes a time reversal. And you glue it at chi. And now we have a complete initial data slice, which is the union of sigma and sigma tilde here. So now we have initial data, and we can evolve forward and backward in time to get some full space-time. And as you see here, I've drawn some red lines emanating from the QES because in general, shocks will be introduced here. The reason is that when you're not working at the classical level, the QES is of course not an extremal surface in the sense that the area variations do not vanish. So the junction conditions will lead to shocks. And exactly how it works, the shocks work out is worked out in this paper here. Great, so now we know how this works. So now let's just go ahead and canonically purify some evaporating black holes. So let's consider the usual picture. So we take a one-sided ADS black hole from collapse. At some point, we turn on absorbing boundary conditions and dump the Hawking radiation into some reservoir. And then we know that before the page time, the dominant QES is just the empty set, and a Cauchy slice of the entanglement wedge with respect to the state living at this time here is just a complete Cauchy slice, which is, for example, this black one here. After page time, we have the usual island QS, and a Cauchy slice of the entanglement wedge is this blue Cauchy slice here for the entanglement wedge. Okay, so just to introduce some notation. So on the left, I've drawn the boundary or the microscopic picture. So with capital letters subscript on the density matrices, that means the microscopic state, so the CFT state or the microscopic state of the reservoir. And on the right, I've drawn the bulk picture or the effective picture. So of course, the blue here is dual to the blue here, and the orange here is dual to the orange here. So let's go ahead and do this procedure. So you start with a full state on the black hole and the radiation, trace out the radiation. The state is dual to this slice. We canonically purify, which is just gluing to, take a second copy of this Cauchy slice, glue it to itself, evolve forwards and backwards in time, and we get this short Lorentzian wormhole. And here, say we have evolved with reflecting boundary conditions. Okay, so here comes the interesting observation. So just consider some state rho b of some quantum system, and let phi br and psi br be any two purifications of rho b on the same Hilbert space. Then it's the case that phi and psi are related with a unitary that acts only on the system R that purifies B. So what does that mean for us? Well, we know that both the original state, which was dual to this picture, and the canonically purified state, this one, they're both purifications of this density matrix rho BH. So that means that there exists some unitary acting only on the radiation that takes it from this picture to this picture. But this is exactly the statement of ER equals EPR in the context of an evaporating black hole. So we see there indeed exists a URAD that converts the entanglement between the late time Hawking radiation and the black hole into a semi-classical ERB. That's nice. Another convenient thing is that this allows the computation of SRAD, so the von Neumann entropy of the radiation with just the standard QES formula. Because the von Neumann entropy of the radiation is unitarily invariant, so we can conjugate with this unitary that takes us to the canonical purification. So this is the von Neumann entropy of the density matrix reduced to this system here. But here we're just doing normal holography. So we can just use the ordinary QES formula. So it's the generalized entropy of chi. So you can bypass the kind of confusing aspects of the island formula with like relaxing the homology constraint and all of this. And you can also use this to compute other things like Renyi entropies.
Can I make a comment?
Sure.
Yeah, this is sort of doesn't contradict anything you're saying. I just feel like it's wrong to say that the standard QES formula doesn't already include the island prescription. I mean, in particular, islands satisfy the homology constraint. So they were always mandatory. It was not really optional when you try to find the smallest generalized entropy quantum extremal surface.
Okay, sure. Yeah, I think I'm happy with that. Okay, so yeah, in the paper we computed one of these canonically purified spacetimes explicitly in JT gravity. The formulas are pretty messy. I'm going to spare you the details. I'm just going to draw conformal diagram here. So I guess the interesting thing is to look at the shocks. So as I advertised earlier, there will be shocks emitted from the QES, and you see that these shocks passing through here. One of them will actually have negative null energy, but you can compute that the Anik holds. So this looks like a very sensible space-time. You actually also get shocks emitted from the conformal boundary because you took the state at a time where reflecting boundary conditions didn't hold. So here we evolved with reflecting boundary conditions, which sounds like a contradiction, but essentially what we do is like we turn off the reflecting boundary conditions over a very small time window and take that window to 0. But you don't even need to choose reflecting boundary conditions. You can do something else if you like, because still this domain of dependence here is gonna be the same. So everything that's like contained in the center of the diagram doesn't care about those boundary conditions. Okay, so what was crucial for these stories was that Cauchy slices of the entanglement wedge of the black hole, that they are incomplete. So let's look at the picture before the page time. So you do the same thing, you start with the state on the black hole and radiation, trace out the radiation, canonically purify, which is gluing along the QES and evolving forward and backward in time. But of course, the QES is empty, so you just introduce a second copy of the Cauchy slice. So you just get this disconnected space-time of two one-sided black holes where the bulk matter is entangled in these two universes. Now, just as a side note, kind of this nice application of this picture is that it geometrizes the fact that unitaries on the radiation can affect the infalling observer only after the page time. But anyway, so what does this mean for ER equals CPR? The fact that we find this disconnected geometry before the page time. So what we see is that collapsing the radiation into a black hole does not always lead to an ERB, even when there is a semi-classical dual. I think often many of us, at least I had at some point, the kind of intuition that if I took the Hawking radiation just before the page time and collapsed to the black hole, I assumed, yeah, we get an ERB, but this is not necessarily true. Now, there could still exist some factorized unitary such that we act on this system and get a wormhole. I haven't said that such a thing doesn't exist, and probably it does exist. And if that does exist, then of course we can just compose that with the unitary that we use to go to the canonical purification, and we get this picture.
Sorry, Aasmund?
Yeah.
I forgot whether in this setting, you've still extracted the radiation, the early radiation from the space-time, right? So,
yeah.
So the entropy in the space-time is equal to that of the radiation, and it comes from the inside Hawking partners.
Yeah.
Okay. So you're contemplating a unitary acting on those?
You mean this unitary is here?
Yeah.
Yeah, so essentially one is acting on, the CFT, and one is acting on the reservoir, which here is equal to the radiation. But okay, we map the reservoir into this second CFT essentially. I'm not sure if I answered the question properly here.
Yeah, thanks.
Okay. Okay, but the important thing to note here is that we need this VBH to not be the identity. Because if this VBH here was the identity, then this BH system would retain a complete Cauchy slice, so we could never get to this picture. We certainly need to change something about the entanglement wedge of the BH system here. So the lesson is that to realize ER equals CPR with a semi-classical wormhole before the page time, we are forced to modify the original black hole as well. Acting purely on the radiation will not work if you believe the usual things about entanglement wedges. Another thing that's worth noting is that derivations, quote unquote, of ER equals CPR using the geodesic approximation only work in the strictly classical limit, and they give the wrong result with quantum corrections. So now let's look at the little puzzle. We look at the page curve. We take two times, T1 and T2, a little before and a little after page time, where the von Neumann entropy of the black hole, or of the radiation, if you like, is the same. We form the canonical purifications and we get these two different spacetimes. Now, of course, these two spacetimes have the same amount of entanglement. So what is causing the difference between these two? Of course, classically, if there's no bulk matter entanglement, we know that the mutual information being order 1 over Gn is equivalent to AB having a connected entanglement wedge. This is pretty easy to see because if the mutual information is non-zero, then this term is non-zero, and it means that XAB, so the HRT surface for the AB system, is different from the union of the HRT surface for the individual systems. And that means that XAB has to lead to a connected entanglement wedge, because if XAB wasn't actually causing this connection to happen here, but if XAB was the union of these two gray surfaces, XA prime and XB prime, that would lead to a contradiction, because then these XA prime and XB prime would be the HRT surfaces of A and B alone in the first place. But this breaks down immediately with bulk quantum corrections, because here the mutual information, since we have a bipartite pure state, it's just the same as 2 times the von Neumann entropy of either of the systems. So this is not a diagnostic that works anymore. So maybe there is something else. Maybe it's the degree of mixedness of the state in some sense. So maybe it's, say, for the black hole, the difference in the thermal entropy versus the von Neumann entropy, the black hole, which is non-zero and fairly large before the page time, if you're not too close to the page time, and it's approximately zero after page time, essentially by definition of the page time. So maybe we need that delta S is small for connectivity. Turns out that that can't be right. So we can throw some pure matter into an old black hole, and we can increase the thermal entropy by a lot if we want. But the von Neumann entropy doesn't change if this is a pure state we're throwing in. And the QES remains non-empty. So the connectivity of the canonical purification is unchanged. This is not too hard to see because the von Neumann entropy of rho with extra pure matter is the same as the von Neumann entropy of the original state rho before you threw in the pure matter. And we knew that this was less than the generalized entropy of the empty set, which doesn't change when we throw in this matter. How about complexity? So if you look at the canonical purification before the page time, we see that there are some non-minimal QESs there. And from the story of the Python's lunch, we know that these regions should be exponentially hard to reconstruct. While if you look at the post-page time wormhole, there are no such QESs. So it's like a short wormhole, should be simple to reconstruct this Cauchy slice. But that's probably not the answer, because we have other examples where we have connectedness in regions that are exponentially hard to reconstruct. Complexity doesn't seem to be able to discriminate these various cases. So the question is, what determines connectivity? We can construct two states with semi-classical duals with the same amount of bipartite entanglement or mutual information, complexity, degree of mixedness. One is connected, the other is not. Let's just look at one more example that is essentially just the same puzzle. It's just maybe a nice arena to look at this puzzle in the future. So just let's now take the evaporating black hole, but we'll just make it two-sided. And then we evaporate just the right side. Early on, again, the Cauchy slice is complete, we canonically purify, and now all the entanglement is mediated by just bulk entanglement, then you just introduce a second copy of the system. Post page time, we have this non-empty QES, And now canonically purifying, we take a second copy of this slice, glue it to itself, second copy of that slice, glue it to itself, and we get something like this. And now L connects to the L tilde that we introduced, and R connects to the R tilde we introduced here. So again, what property of this state determines which subsystem connects to which. So let me summarize and speculate a little. So we show that the connectivity of the canonical purification of an evaporating black hole changes at the page time. We show that the general procedure to implement ER equals EPR after the page time exists, assuming that the islands are general things in evaporating black holes. We have shown that acting purely on the radiation before the page time cannot build a semi-classical ERB. You also have to do something with your original black hole. And we have highlighted that diagnosing connectivity is qualitatively different once subleading one-rank corrections are included, or maybe more appropriately once bulk matter entanglement is included. So it could maybe be that multipartite measures could tell us something that could be interesting to study in this state, various measures between the various systems here. Or maybe you could think that the spectrum of all the Renyi entropies could tell us something, because maybe you think that this should know everything, because if you know rho, you have all the info you need to get the canonical purification. And you know a lot about rho when you know this whole series. But actually this cannot tell us whether you have a connectivity or not if this kind of weak version of ER equals EPR that I've written here is true. And namely that there exists a factorized unitary that you can act with in order to create a connected semi-classical dual. The reason is that the spectrum cannot work if ER equals EPR is true, since if we can map the pre-page canonical purification to a connected spacetime with a factorized unitary, that means we can map a disconnected spacetime to a connected spacetime without changing the spectrum. So we can go from a disconnected to a connected spacetime while keeping this spectrum fixed, because this spectrum is unitarily invariant. Okay, that's what I have. Thank you. Any questions?
Any questions for Aasmund?
Do you, I mean, Juan is here, so he can correct me, but I would have thought that ER equals EPR was supposed to mean in particular that when you have a bunch of particles, for example, that are entangled with one another, that, well, we all know that there's no real wormhole, but we're allowed to think of the entanglement in terms of maybe sub-Planckian or Planckian wormholes. You're not, that's compatible with your lower example here, right?
Yeah, it is. I think, you know, I'm not claiming that this proposal 2 is like capturing all of ER equals EPR, but I think any reasonable interpretation of ER equals EPR should imply that weaker statement. You know, if you have a bunch of those particles with these highly quantum wormholes, it should be able to like maybe collapse all those, you know, particles into black holes, and then all of these like quantum wormholes maybe like condense together and form a big wormhole or something like that. I mean, yeah, if someone thinks this is, yeah, to me, it seems like kind of a, I can't think of a version of ER equals EPR that shouldn't imply this proposal 2.
So I was wondering whether to distinguish between the two cases, you couldn't look at some property of the modular Hamiltonian, but maybe that's the same as looking at the spectrum of the.
Yeah, we actually, yeah, some of us have been talking about actually some of that last week. So I think, yeah, that is probably the most promising avenue to go down, to do something with the modular Hamiltonian. Yeah.
The full modular Hamiltonian, not the half-sided guy, because the half-sided guy. Yeah. Any other questions? Okay, if not, let's thank Aasmund again.